Welcome class for the week 7 tutorial video. I'm going to be specifically highlighting StatCrunch features, but I want to talk very briefly at the beginning about this idea of a theoretical model, or the theory behind the linear regression, which we didn't really get into in detail last week. And again, this is going to be just a brief overview of it, but it'll clarify some of the notation that you'll see in the homework. So when we have a linear relationship between a y variable and an x variable, this is what we're really saying. So this variable y is this is what I'm going to call like the true relationship. Y is going to be some beta 0, some constant number, plus beta 1 x plus e epsilon. So the beta 0 and the beta 1, these are what we call parameters of the of this relationship, whereas epsilon is actually a random variable. It's random. I'll call it noise. So for every time we have an observation where x is some value, we have this linear relationship with the intercept and the slope, but also we add to it some random noise. This is why when we plot these lines of best fit, it's never perfect. There's always some variability. Now the model, what we're actually estimating, is what I'll write y hat equals b0 plus b1x. So whereas we have parameters beta 0 and beta 1, we have only estimates of b0 and b1. Okay, and there's no estimate for the random variable noise. For our estimates, we would estimate this epsilon as being 0, because the assumption is that on average it is 0. Okay, it's random noise. It's in fact it's normal, a normal distribution by assumption that it has some variability to it, but it has a mean equal to 0. Like the distribution of this random variable has a 0 mean. Okay, so what we were really looking at in the previous module was this kind of a linear model. We weren't thinking about the random noise, and we weren't thinking about the betas, but really when we have the intercept and the slope, they correspond with beta 0 and beta 1. Okay? Okay, so now looking at problem 4, when we say we have a small data set and we're asked use technology to find the estimates of beta 0 and beta 1. Remember, beta 0 is referring to the intercept and beta 1 to the slope. So let's go back to StatCrunch. Let's open this data in StatCrunch and just refresh us on how we'll do the linear regression in StatCrunch. Okay, so we have our data. Go under Stat, Regression, Simple Linear Regression. You select your x variable, you select your y variable, and what I'm going to do is, well, I'll just hit compute. I don't know what else the problem's going to ask for. For now, I'll just hit compute and we'll get our output. Okay, so we've got an intercept and a slope. So the intercept is what we would call beta 0, or sorry, b0 is the estimate of beta 0. And then b1, slope, negative 0.7. Compute the standard error, the point estimate for sigma. Sigma is the estimate for the standard deviation of the random error. So the standard error is going to be up here, error standard deviation. When you see it right here, the estimate of error standard deviation, that is what we're asked for right here. So 4 decimal places takes us to 3.3065, which I have to round up to 66. Assuming the residuals are normally distributed, use technology to determine the standard error of beta 1. So this is actually given right here. Estimate the standard error to determine the sample standard error of B1. That's the slope, and it's given right here, 4 decimal places. Say the standard error for the slope coefficient, and I have to round that up to 6. And assuming the residuals are normally distributed, test the null hypothesis beta 1 equals 0 versus the alternative that beta 1 is not equal to 0 at alpha equals 0.05 using a p-value. This question is really, we look right here at this line in the linear regression output. So it gives his alternative not equals to 0, it gives a t-stat, and it gives a p-value. This little bit here is addressing this hypothesis test question. So this is answering the question for us. If you're doing a null hypothesis where the null is the slope is equal to 0 and the alternative is not equal to 0, the p-value for that test is given right here. 3 decimal places would be 0.007 rounded up. 0.007, which means there's very, very strong evidence in favor of the alternative, which is that the slope is not 0, which is to say that this is the slope, right? This is asking whether or not these two variables, x and y, if there's a statistically significant linear relationship. Okay? Anyway, we would reject the null and conclude that a linear relationship does exist between x and y. Okay, great. Okay, another table of data. Let's open this up, bring it into StatCrunch. And it says this is the rate of a company's stock for 11 months compared with the rate of return. Both are in percent. Okay, so we're going to first use linear regression to find the coefficients for our model. So our x variable, you can see x is right there, y, and let's compute. Okay, so remember B0 is the intercept. It's an estimate of beta 0, and it is 1.23. It's going to be 1.2377. I have to round up 4 decimal places. Estimate of B1, 4 decimal places, right there. Sorry, the estimate of beta 1. All right, let's see. Assuming the residuals are normally distributed, test whether a linear relationship exists, and so whether or not a linear relationship exists, the correct alternative is not equal to. So this is what we want. The null hypothesis, no, but we're not testing on beta 0, we're testing on beta 1, the slope. Beta 0 is the intercept, we're not testing that. Equal 0 versus not equal to 0. That's the hypothesis test. And the p-value, it's right here, 0.026. Linear regression output performs a similar hypothesis test calculation for the intercept as well. It's usually not such a crucial question, but you can actually see the p-value for the intercept is not that low. So although we estimated 1.23, we wouldn't say that that estimate of the slope is statistically significant. So the model could actually have the intercept be equal to 0, and we wouldn't consider that to be, that we would consider that to be fine. There's not enough evidence from our data to be statistically convinced that the intercept isn't 0. Okay. But anyway, for the slope, yeah, that's definitely a low p-value, especially compared to 0.10. So we would reject H0. There is sufficient evidence to conclude a linear relationship exists between these two things. Okay, let's see what's next. Okay, let's do a confidence interval for the true slope. Now, we can actually, when we were running the linear regression, we had the option of either doing a hypothesis test or performing confidence intervals. So I'm going to construct confidence intervals, and I'm going to do it at a 90% level. What that's going to do, instead of giving us p-values for the intercept and the slope, it's giving us a confidence interval for the estimates. Look at that. That's beautiful. For the slope, the 4 decimal estimate, I'll just copy it right there. And I'm going to round that up to 1.2955. Notice the 90% confidence interval, which it's kind of the flip side to a hypothesis test at the 10% alpha level. This confidence interval doesn't span the 0. It's all in the positive numbers. So as opposed to the intercept, it goes from negative 0.5 to positive 3, which means you can't be 90% confident that the intercept isn't 0, but we could be 90% confident that the slope isn't 0, right? And that corresponds with rejecting the null hypothesis that the slope is 0. Let's check that. Okay. Okay, now I want to show you predictions and how to do that again from StatCrunch. I'm going to go back to edit and show you, if you just go a little bit below, a prediction of y. You can put in an x value or values and get a prediction for y. I'm going to put in 3.45, and the level isn't so important right now. It'll give you a prediction interval in addition to the point prediction, but that's all I really care about is the point prediction. So put in 3.45, and it'll give me the similar output, but just with one additional section. If I scroll down, the predicted value for an x value of 3.45, the predicted y value is given right here, 3.8807. So I'm going to round that to 3.881. It also is giving me the standard error of this prediction and a 95% confidence interval for the mean and for new. This is something that's a little beyond this course, but the idea would be, well, I'll leave that. I don't want to get into anything more complicated. Confidence intervals and prediction intervals are another interesting aspect of this, but we're not going to get into it right now. Okay, but this is good. Okay, so that's how you can do predictions for a linear model from StatCrunch. We did it before directly from the calculator, but this way you don't have to copy and retype in those intercepts. Okay, so let's see what we got for this problem. I'm going to again start by copying this into StatCrunch. We've got determine if there's a relationship between HDL and age. Okay, so draw a scatter diagram of the data treating age explanatory variable. What type of relation is there? Okay, so based on a scatter plot, let's graph. Remember how to do a scatter plot. Under graph, scatter plot. The x variable is age is explanatory. It labels it as being y. Remember, the explanatory is always the y variable. And I'm going to just leave things as they are. I'm not going to add any of these options. Based on the scatter plot, we want to decide whether or not there is a linear relationship. This looks like a big old mess. I don't see any sort of trend line. I would say there appears to not be a relation, at least from a visual, inspection. The least square regression example. So this is to say, okay, well, let's for the sake of argument do a linear regression and just see what we would get. Simple linear regression. Okay, you're used to it by now. Age, cholesterol, hit compute. Okay, so we have our estimate for the slope and the intercept. Remember, this thing wants me to put the slope in first. The slope is times x, so I'm going to copy it with 3 decimal places of precision. And the intercept is what we're adding. Okay. Are there any outliers or influential observations? Well, what we would let's see, to answer that, let's go back to edit, and I'm going to graph the fitted line plot, and that's what I'm going to do. Compute. That option I think was already on. If I had clicked right, I would have gotten this. So anything influential is something that is particularly far away from the trend line, but because everything is pretty spread out anyway. I mean, this one point would be influential if the rest of this stuff wasn't so didn't have such a poor trend line to begin with. But because it's also poor, I would say that there really isn't any influential observations. Okay. Test whether a linear relationship exists between age and HDL. So remember, a linear relationship has to do with the slope coefficient, and the alternative is always not equal to. And the p-value, that's from the previous page. The p-value for slope is given over here, 0.795, that's 0.796 rounded up. And that's a pretty hefty p-value. That's means the data lends us to put our belief in the null hypothesis. It's very probable the null hypothesis is the case based on the data that we have. So we would not reject the null hypothesis. The p-value was greater than our significance level. It's much greater. We would need a very, very small p-value to reject, and this is a whopping p-value. Okay, let's do the confidence intervals. Remember, we go to the options, edit, and change from hypothesis test to confidence interval, 95% confidence interval. That's all we need. For the slope, we have our lower bound, 3 decimal places, and upper bound, 0.385. So this is a great example where this confidence interval, it spans 0, and so we couldn't say with 95% confidence that the slope isn't 0, right? Let's see. For a 42-year-old male patient who visits the doctor would using the least squares regression line obtained in part B predict the HDL cholesterol of the patient be recommended? So basically, we wouldn't recommend using this model. So since since we didn't reject the null hypothesis, right? That the null hypothesis was that there is no linear relationship, and we didn't reject that, which means the linear model, is not something we want to put our belief in. Okay. A good estimate for HDL cholesterol. So if we reject the linear model, the best way to make a prediction would just be to take all of the cholesterols for all these patients, and I'm going to just get an average of them. That would be the best prediction. I'm going to just take HDL cholesterol and just compute the mean of the sample, 44.71. We don't want to employ the linear model for prediction. We're just going to simply average the data. Okay, so let's talk a little bit about the multiple linear regression models. So if we have our model y hat is 1.83x1 plus 8.43x2 plus 28.06. Okay, these coefficients, whatever x1 and x2 refer to, and there's no context in this problem, so they could be anything, but the idea is if we were able to control for x2, like hold it constant, and just change the value of x1 by 1 unit, so what do we have here? If x1 decreases by 1 unit, then the response will decrease by blank units. Well, if x1 increased by 1 unit, we would expect an increase of 1.83 for the response. But if it decreases by 1 unit, we would expect a decrease of 1.83. Oops, 3. Okay. So looking at this other model, y hat is 10 plus 3x1 minus 4x2. So the slope coefficient for x1, so it's 3. Okay, the slope coefficient is 3 for x1. So for every 1 unit increase of x1, if x2 is held constant, we would expect the response to increase by 3. That's what this first option is saying. Okay, and for x2, since it's negative, we would expect if x2 was to increase by 1 unit, we would expect the response to decrease by 4 units. That's what we have here. Decrease it for every 1 unit increase in x2, as long as x1 is somehow held constant. Okay, now what if we hold, if x1 is equal to 10, then what is this regression line? So if x1 is equal to 10, let's just power on our calculator. Let's just, I think we may have to reset it. Okay, so we want to just check if x1 is 10, so we'd have 10 plus 3 times 10, we would have 40, so it would be 10, it would be 40 minus 4x2. And let's see, what do we have next? What would that look like? Well, now, if you're not very strong in graphing a line, that's okay. It's good to know this is a intercept and the slope. But I'm going to show you, there's a good website, Desmos graphing calculator, desmos.com/calculator. If you want to do a very quick graph of some function like this, you can just type it in and it'll graph it for you. Y equals 40 minus 4x, and you can see it's already showing up. We can scroll out a little bit or zoom out. So this is the picture we wanted, and you can see this gives a little dot at the intercept here and here. So let's just compare. It's either this or this. Let's just look at this one first. This one, no, that's at 80. We should be crossing at 40, so this is no good. Let's check this one out. Yeah, this is good. It crosses at 40, and over here at what looks like 10. That matches up. That's good. So let's check it. Okay, a regression equation if x1 equals 15. So let's go back to our calculator. If x1 is 15, we would have 10 plus 3 times 15. 10 plus 3 times 15 minus 4x2. That's 55. So it's a 55 minus 4x2. Okay. And let's see. And we want to check what that's going to look like. Well, again, let's just put it in here. Let's change it from 40 to 55. And sure enough, right, we've got an intercept at 55, and we've got this crossing at, well, 13.75. Okay. It's one of these two. Let's just see. That one looks pretty good. It should be crossing at, yeah, 55. There's 50, and that's 60. So it's right halfway between. That looks good. So we'll go with it. Okay, regression equation x1 equals 20. Okay, so well, this looks like more of the same. But just for argument's sake, if x1 equals 20, we're going to have 10 plus 3 times 20. The intercept is going to be 70. Okay, and let's see. Okay, that's going to the slope is going to be the same. It looks like this is probably it. We want to have a 70 slope or 70 intercept. Yeah, that looks fine. So clearly what you can see, the effect of changing the value x1 changes the y-intercept. Okay. All right, let's go to 10. And 10 we're going to look at actually building a multiple linear model using StatCrunch. So they're giving us a table of data with your x1 variable, your x2 variable, and your y. So we're going to load this up in StatCrunch. So we're looking at air temperature and speed, and we're trying to predict wind chill based on those. So under stat, we want to go down to regression, but choose multiple linear instead of simple linear. So for the y variable, we want to pick y. X variables, pick x1, x2. Leave your interactions blank. This is something that we might get into later, but we're not putting interaction terms into our model. And that's it for now. Just hit compute, and we'll look at the output. We have our intercept, and we have, let's see, 3 decimal places. I can do that. x1, I can just type it in 1.334, and x2 negative 0.414. Everything looks good. let's see, a residual plot to assess the adequacy of the model, residual plot for air temperature. So what we'd want to have is across the x-axis we want air temperature, and across y-axis we want those to be the size of the residuals. So to do this, what we're going to do is go back to edit the options of our regression model, and I'm going to scroll down a little ways, and I want to it doesn't, as far as I know, have a way to generate the graph that we want directly. So what we're going to do is we're going to click Save Residuals, and what that's going to do for us, it will create a new column in our data, in our spreadsheet down here. Can you go away? I know it's hanging around. Okay, let's close it. So you can see my residuals are now saved now. So what I can do, I can plot residuals against x1, which is, remember, x1 air temperature is x1. So I'm going to go to graph. I'm going to just do a scatter plot of my x variable is x1, y variable is residuals, and just hit compute, and I'm going to compare this to these scatter plots and see what it looks like. Okay, so it goes from -30 to 30, and 0 is here, and we have that like high point. It looks like this is the one. Let's just check it out. See, the 0 line is going across there. That looks good. Those are goes up to, this point is just below 8. So yeah, everything looks great here. This is the residual plot. Oops, that's the one. All right, residual plot for wind speed. So I'm going to go back to options, edit this, and I'm going to change the x variable from x1 to x2. So we're plotting the residuals against wind speed now. Let's see. Okay, so I think that it's pretty clear which one that is. You can see this shape. This is what this would be a red flag that says, oh, there is the relationship between wind chill and x2 is not linear. These residuals are not what you would see from a linear relationship. Yeah, the plot shows a discernible pattern. This kind of a curve is a discernible pattern, and so a linear model is not appropriate. That's what we would conclude from that. Okay, so that was doing multiple linear regression in StatCrunch, as well as some of these other prediction and plotting residual plots. All right, good luck with the homework this week, and I will be in touch. If there's any questions, please drop me a line. All right.